I had a great temptation about my title. I was thinking about giving a title like Prashant Chandra Mahalanobis, the accidental statistician. But I felt a little nervous about possible political sensitivity of it. But I think the way Prashant Chandra Mahalanobis became a statistician and then developed a lot of things that are considered still most fundamental contributions in statistics, they happened accidentally. So there is nothing wrong in calling him an accidental statistician. I will begin with the first accident. How come Prashant Chandra Mahalanobis become interested in statistics? He was born in 1893, and after completion of his undergraduate, he went to Cambridge in 1913. He completed Part 1 Tripos in mathematics, performed very badly, had a third class. Nobody knows about it. Keep it a secret. Okay. Then he switched to natural science, which is mainly in physics, and stood first class first in physics, and got a scholarship. And with that scholarship, he set up a project in Cavendish lab under the supervision of C.T.R. Wilson and J.J. Thomson. And then in 1915, he decided to take a vacation to return to India during summer. He never went back and became interested in statistics. Now, why that happened? Now, there are some popular saying about it, but most of them are not right. Like, you will hear things like that. On his way back, he brought this 9 volumes of Biometrica, at that time edited by the famous statistician Carl Pearson, and that made him a statistician. It's not, okay? There was a very interesting quote-unquote accident in his life that made him a statistician. So he returned here in 1915 summer. So he went to Darjeeling with his family members, and there he met his future wife Nirmal Kumari Mahalanobis. They were both from Brahmo society, but Prashant Chandra was sort of part of the more young liberal Brahmos, whereas Nirmal Kumari's family was on the more conservative side, particularly Nirmal Kumari's father, Hiram Chandra Mitra. So, Prashant Chandra, in spite of being a very deserving groom, was not liked by the prospective bride's father. And that landed young Prashant Chandra into a quote-unquote crisis in his life. So that's the first accident. Now, in Prashant Chandra Mahalanobis' life, one person who had tremendous influence was the famous Nobel laureate poet Rabindranath Tagore. He was very close to Rabindranath Tagore, and these two people, in spite of big difference in their age, used to share a lot of their emotional issues and various likings and dislikings. So when this problem started with his would-be wife, obviously he went to Rabindranath. Or he went to two people actually, Rabindranath, and the other person was his uncle, Subodh Chandra, who was a professor of physiology in Presidency College at that time. Because of his personal problem, Prashant Chandra did not want to return to England, and so Subodh Chandra worked out a part-time position for him in Presidency. He started teaching physics there as a part-time teacher. Rabindranath gave him a very interesting suggestion. Rabindranath said, look, you are now mature. There was a point of time I could give you advice and things, but now I think you need advice, more solid advice than what I can give you. So please go and meet Acharya Brajendranath Shil. Acharya Brajendranath Shil was the professor of philosophy, and he was an expert on many things. At that time, in Calcutta University, was involved in the review of the curriculum. And he asked Prashant Chandra to look at the marks obtained by various students in different examinations and gave him some specific instruction how to analyze such a data. So that was his first statistical assignment. And if you go to our archive, you'll see some handwritten documents. That project never finished properly because Brajendranath Shil got transferred to Mysore. And so that project sort of had a premature end, but you see some very interesting calculations by Prashant Chandra Mahalanobis in some notes there. Okay. So that's the first accident that made him getting closer to statistics. So in 1920, he met Nelson Annandale. Nelson Annandale at that time was the director of Indian Museum. So you see, the first paper that Mahalanobis wrote, it was published in Records of Indian Museum. This is the journal that Nelson and Nandal started in 1907. So he came to India in 1904 and he started this journal. He gave this data on Anglo-Indians to Prashant Chandra Mahalanobis, which led eventually to the invention of Mahalanobis' famous disk square statistic. So that's the first paper. And this 1930 paper in Journal of Asiatic Society is sort of the paper that we usually cite when we cite Mahalanobis' work, because this has all the details of the theory and methodology that was done by Prashant Chandra Mahalanobis. Subsequently, the theoretical work was done by a very famous statistician and a very famous physicist. The statistician was Raj Chandra Bose and the physicist was another Bose, Satyendranath Bose. These two people developed the statistical distribution theory of Mahalanobis distance for the first time, but their analysis is completely unreadable for today's students because it doesn't use the modern multivariate and probability tools. It's all classical analysis involving Bessel functions and such things. Derivations that we teach today, that's due to Somarendranath Rai, and that's a lot more comprehensible. But this led to another event, which again I can call some kind of an accident. This paper that appeared in Records of Indian Museum, Nelson Anandal sent it for review to a very famous applied mathematician named Gilbert Walker. In statistics, we know his name in the context of Ewell-Walker equation. He came to India with Nelson Anandal in the same year, 1904, and he came as the Director General of the observatories. So he was with the Met Department. He was asked to review this paper. As the in charge of the Met Department, he also was involved in a lot of analysis of a huge amount of meteorological data, and Nelson Anandal thought he would be the right person to review Mahalanobis' work, and that's how it went to Gilbert Walker. And Gilbert Walker immediately saw the potential of the work and offered Prashant Chandra Mahalanobis the job of chief meteorologist in Alipur Observatory. So from 1922 to 1926-27, Prashant Chandra Mahalanobis actually had two jobs. He was teaching in residency. That was really a part-time job for him, but he was the chief meteorologist at Alipur Observatory in Calcutta. That's the second accident. And when he was working on that, I'll briefly mention two things that happened. There was a famous British meteorologist named William Henry Dines. In 1919, he wrote a very interesting paper. So he designed a device which you put in a balloon and shoot it into the sky, and it moved up, and then that device was taking measurements at different heights, and based on the data that Dines collected in 1919, he published a paper where he claimed that the atmospheric activities like rains that we see near Earth's surface, that correlates very highly with the temperature at a height of 9 kilometers. So 9 kilometers, the magic number. Okay, apart from this 9 kilometers, that's quite a bit of height. And why it should correlate at such a height, it was mystery. Prashant Chandra Mahalanobis, as he was working as the chief meteorologist, he was getting involved in such things. So Prashant Chandra realized what was the mistake that Dines was making. In statistics, this is the kind of error that you make when you try to conclude causality from statistical correlation. So this is a very old type of mistake that scientists make again and again, and Dines was making the same mistake. It's something like this, that if I have a very large population and I collect data on people's income and their blood pressure, I will see a very high correlation. That does not mean high income is causing high blood pressure. That happens because there is a hidden variable called age. Income correlates highly with age, because as you grow older, you probably earn more, and as you grow older, your blood pressure tends to grow higher also. But if you adjust for correlation with age, you'll see a very low correlation between income and blood pressure. So it is the hidden factor age. So what Dines was missing is you have this balloon shoot up and it was coming down, and there was a very high serial correlation at different heights. Now, if you want to calculate correlation of activities at different heights, you have to adjust for that serial correlation. And once you adjust for that, you see there is very little correlation at the height 9 kilometers as it is supposed to be. Most of the correlations are at the height of 1 kilometer or 2 kilometers, which makes perfect sense. Gilbert Walker gave Mahalanobis a good advice. Don't send it to British Journal. Publish it in Memoirs of Indian Met Department, which also was started by Gilbert. But of course, it was noticed by the British meteorologist. And in Nature, in the year 1923, May, there was a long article by Dines trying to tear apart Mahalanobis' theory. Then Mahalanobis made a response to that, and that was a very well-written response explaining things. And now everybody realizes the mistake that Dines was making. Okay? So this is an interesting incident. And it actually shows that from a very early age, Prashant Chandra had that uncanny feeling for data and how to interpret results from statistical analysis. By 1923, his problem concerning marriage with Nirmal Kumari was settled. Then he wanted to go back to England. So he quit his job in 1926, took a leave from his teaching job, and decided to go to England. And in 1927, he actually returned to England, but he went there to meet a very famous statistician, and I will come to that. So this is from Mahalanobis' own writing. In 1923, I was working as meteorologist in Calcutta in addition to teaching physics in Calcutta. Fisher was engaged in his researches on the design of experiment at Rothamsted, and I had no connection with agricultural research. But because of his connection with the Met Department, he got interested in agriculture, and that made him write a paper. The way Fisher noticed it, because Fisher was the reviewer of his paper. Fisher saw this paper and immediately sent me reprints of his early papers on the design of experiment and also the paper on the distribution of ratio of two variables, the famous F statistic. That was the beginning of a very long and fruitful friendship between two stalwarts in statistics, Ronald Fisher and Prashant Chandra Mahalanobis. I, with the help of another person, went through some of the correspondence between Fisher and Mahalanobis, and the evolution of their relationship is very interesting. Before 1930, Fisher would always address Mahalanobis as Dear Professor Mahalanobis. Then it becomes, after 1930, 1940, then it becomes Dear Mahalanobis. And from 50 onwards, Dear Prashanto or My Dear Prashanto. So that's how the relationship evolved. Fisher came to India 9 times altogether as far as my count goes. The last visit was shortly before he passed away in 1962. So from here he went to Australia, where he was working with Cornish on this Cornish-Fisher expansion. That was the last time he came. Okay. Now in the same article from which I have quoted, Mahalanobis writes, so I also recall that it was at Fisher's suggestion, as I came to know much later, that the newly established Imperial, now it is called the Indian Council of Agricultural Research, offered me in 1928 an annual grant of rupees 2,500, a princely sum for us in those days, to have a research assistant to take up some work in statistics. And this grant led the way to the future development of the integrated program of theoretical research, training and applied projects, which has been a characteristic feature of the Indian Statistical Institute. Fisher's grant was a SIG money for Indian Statistical Institute. Well, I shouldn't say it is Fisher's grant, it is the grant from ICAR given with the initiation of Ronald Fisher. So in March 1936, because this grant was coming from Agricultural Council, so naturally they wanted some help and service from Mahalanobis. So in March 1936, he writes, in reply to an inquiry from the Secretary Imperial Council of Agricultural Research, I suggested exploring the possibilities of random sampling methods for estimating the area under different crops in Bengal. So that was the beginning of his involvement in sample survey. So he started with agricultural survey. I have listed these because these are sort of the prime contributions of Mahalanobis in sample survey. One was this optimum design of the surveys, maximizing precision at a given cost or minimizing cost for assigned precision. So it's solved an operation research problem. This concept of pilot survey and interpenetrating network of subsamples or IPNS for the assessment of sampling variations and the control of non-sampling error. So it's like Mahalanobis will send 2 independent surveyors, and then they will come with independent samples, and then they will do some cross-checking, and that will also give how much sampling variation is there. The comment by Harold Hoteling. I will mention the next one, which is also from a very famous statistician who came to India, visit Mahalanobis, and he passed away in an air crash, and so he never went back to the US. So he was coming from Columbia University at that time, and he passed away in a air crash with his wife. He said that the occasional practice of designing a large-scale experiment in successive stages may be regarded as a forerunner of sequential analysis, which he himself developed. His Wald's work on sequential analysis is very fundamental. When you teach undergraduate statistics or postgraduate statistics, so it's usually the Wald's book, which is like the Bible in sequential analysis. And a very interesting example of, he says, of this type is in the series of sample censuses. He used the term sample census instead of sample survey of jute in Bengal carried out under the direction of Prashant Chandra Mahalanobis. And I think Prashant Chandra Mahalanobis's contribution in sample survey will not be complete if I don't tell you the story about the jute survey. So what is the jute survey? Before Prashant Chandra Mahalanobis was involved in agricultural survey, there was another British civil servant who also had a Cambridge connection. His name was John Hubach, who realized that the way the government is collecting data on agricultural product is very faulty, because what used to happen is that a block officer will go and meet the farmers, will have a discussion and come back and will note down some data, which usually was not very accurate. John Hubach started something called the crop cutting experiment. He actually sent surveyors to land, and then a small part of the land will be marked and the crop in that part will be taken out, and the amount of yield will be actually physically measured by some method. Sometimes if it is jute, they will burn it, and from the ashes they will try to measure how much will roughly be the production. So this crop cutting experiment started, which is a more scientific way of making estimation than just this eyeball estimate or having a conversation and giving an estimate based on the farmer's experience. So Mahalanobis adopted that technique, improved Hubach's crop cutting experiment enormously using his statistical skill and ideas. He landed into this famous jute survey of Bengal in 1940. Now, resistance to Mahalanobis' idea was there at that time also, because people were not convinced that doing sampling of only a few plots and doing a little crop cutting experiment, you can come up with a more accurate figure than a complete enumeration of all the lands in Bengal. Okay, at that time it was undivided Bengal in 1940, and jute was the most important cash crop at that time. To tell you the complete story, let's look at some figures. So Mahalanobis conducted the sample survey, and his estimate of jute production was 7,540 bales. It was obtained at a cost of 8 lakh rupees with a workforce of 600. He, because of influence of Fisher and other people, he did manage to get the fund to carry out that big survey. The plot-to-plot complete enumeration yielded a figure of 6,304 bales at an expenditure of 82 lakh. That was the total expenditure for complete enumeration. Now this figure of 33,000 employees is not comparable with 600, because these are actually regular staff in the government. Just like during election we hire some people to do some additional work, these were engaged in survey work from various departments. So they are probably doing other things at other times. So let's not compare that directly. But these rupee figures are comparable. And so it is much lower than what Mahalanobis said. Now the actual figures came to be known much later from the customs and trade figures, because it was a cash crop mainly, and that turned out to be 7,562 bales. Now, in order to get such an accuracy, it's not enough to be a good statistician, you have to be a lucky statistician. Because if you actually calculate the sampling error, margin could have been higher. So Mahalanobis had a bit of luck. Luck was in his favor, and that convinced them, and afterwards flow of funds from the government for that kind of work became substantially easier, though off and on there were problems. When he tried to extend it to the survey of the entire Indian population, there are bigger resistance from different corners. Both of his fundamental contributions, the D-square statistics and large-scale sample survey, the methodological and theoretical development were done before independence, and he became famous by then before independence. So I will now talk about post-independence work. His involvement in planning led to this fractal graphical analysis. Now this fractal graphical analysis Mahalanobis developed for econometric or economic studies, but it has a much wider application. But let me give you a little bit of details about these fractal graphical methods. Mahalanobis was involved with these rural household surveys that generated data on consumption and expenditure, and Mahalanobis was looking into per capita total monthly expenditure for a household and the fraction of expenditure on some specific item like a food. And so it's like, if you look at that fraction, if that fraction is very high, that is an indication that the household is very poor. If most of your expenditure is on food, then you are at the lower strata. Whereas if you are in the upper strata, you will spend only a small fraction of your expenditure on food and you will spend on other things. So these are remarks by Mahalanobis in one of his reports. Okay, so I have taken it and simplified it a little bit because his own writing may not be so easily comprehensible. But the words that he has used, which are critical words, I have retained them and I have put them in quote. So he says there may be important differences in the consumption patterns in the rich and the poor sections of the population. One has to define comparable subsets of the population such as poor, rich, and so on. Individuals in a subset will have similar economic status as defined by ranks with respect to income. Instead of using the variable income or expenditure, he decided to rank households based on that. That gives him two advantages. It's like when he is comparing data coming from two different surveys, because of growth and inflation, expenditure may not be directly comparable unless you make an inflationary adjustment. And he didn't want to get his hands dirty with the inflation model. Instead, he used this intelligent idea of ranking the households so that he has a group of poor households, he has a group of middle class households, a group of rich households, and then compare them. So Mahalanobis divided the data set into these fractile groups. So these fractile groups are these different ranks. And then he plotted the average values of the fraction of expenditure on a specific item. Finally, he joined those consecutive points in the plane by a straight line. I will show you a picture from Mahalanobis' own paper. So you see these fractile graphs. In the vertical axis, you have the fraction of expenditure on food, and here you have these different fractiles for the households, and you have curves for two different rounds of survey, one for 1953, another one for 1955, and he's trying to compare the graphs. Actually, around each main graph, there are two other graphs that he draws. Those are based on two half samples or IPNS. That gives you an idea about the amount of sampling fluctuation that you might have around the graph. This paper, from which I have taken this picture, appeared in Econometrica in 1960, which was a special issue of Econometrica in honor of the first Nobel laureate in economics, Ragnar Frisch, who was also a very good friend of Prashant Chandra Mahalanobis. They had a lot of correspondence. I will just let you read the names there. You will see a lot of future, now past Nobel laureates there. It was almost like a galaxy of stars. And Mahalanobis was one of the authors, and his paper appeared there. Interestingly, in spite of such a high profile issue and such an interesting work, fractal graph is a technology due to Mahalanobis that a lot of people don't know about. And what has happened is that over time, people have used this idea and they have reinvented it. To put it in slightly more technical term, what Mahalanobis was doing is something like this, that if I have a probability distribution for a variable, in fractal regression, instead of regressing y on x, you regress y on f of x. And this f of x, irrespective of what is the f, always has a uniform distribution. And that does a very convenient standardization of the covariate when the covariates are not directly comparable. I will end with one very interesting application of fractal graph that I found in epidemiology, and that was in 1998, 38 years later after Mahalanobis' work. These two epidemiologists reinvented Mahalanobis' fractal transformation. So they were interested in comparing the mortality rate in the black Americans and the white American populations. So what you see in the horizontal axis is the gestational age, and this is the mortality rate. So as you can see that if the baby is prematurely born, then the mortality rate is higher, and more mature birth leads to less mortality, and that there are two curves. They wanted to compare the mortality curves for the two populations, the African Americans and the European Americans. Now, if you compare these two graphs directly, you don't see much difference. Now, if there is not much difference, this paper will not be published, right? Because unless you have a good theory to prove, they will not publish it. These people were very careful statisticians. They looked at the distribution of gestational age, and they see that, okay, so here there are very few births, whereas here most of the births are here. So it's like there are very few very premature births, and then there are a lot of births that are mature births, and so there is a very strong skewness in the distribution, and that you need to adjust. And the only way you can adjust is by making the fractal transformation, which Mahalanobis thought about. And here is what you get when you make a fractal transformation of the covariates, and then you see this white curve is most of the time below the black curve, which proves the difference. And that's why the paper was published. So it's a conversation between Ramakrishna Mukherjee, a very famous sociologist, and Mahalanobis. So Mahalanobis was asking, Ramakrishna, after my death, what will happen to ISI? Would anything survive of what I created? Now Ramakrishna Mukherjee gave this answer. So he says, Professor, your large-scale sample survey will survive. This square will live. Fractal graphical analysis, though I don't quite understand it, will survive if it is useful. And some student of yours will spread your message. Then Mahalanobis paused for a while, and apparently, according to Ramakrishna Mukherjee, Mahalanobis said, Rabindranath used to say, this is a land drained by a river and its tributaries. Nothing survives in this climate for too long. So that's the story of fractal graphical analysis, except one small note I would like to add. Last year, the Nobel Prize in Economics was given to Bill Nordhaus and Romer. The Nobel citation of Bill Nordhaus, it says he is being given the prize for an integrated assessment model. That is a quantitative model that describes the global interplay between the economy and the climate. Okay, how do you measure economy? GDP. How do you measure climate? Temperature, precipitation. Okay, here is your Y GDP, here is your X temperature. You want to study the relationship of this variable. Now, think about GDP as a function of climate. There are several variables. How are you going to compare? How are you going to compare how GDP changes with temperature along with how GDP changes with precipitation? You have to make a standardization of the variable. And for such variables, only transformation is fractal transformation. When Bill Nordhaus, before getting his Nobel Prize, when he was inducted to the US Academy of Science, he gave an inaugural address. And if you look at that article, you will see a lot of fractal graphs. He uses the term fractal graphs. Unfortunately, he doesn't mention Mahalanobis because he doesn't know about this work. He invented it on his own. So I think if you are far ahead of your time, okay, when in 1960 people didn't understand correlation regression, he is doing fractal regression. Of course, people didn't understand what he was doing and it was lost. Now we understand it in 2000, so we are reinventing things. Thank you all for your time.